Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Synopsys with Michael Jackson, who's going to talk today about fusing together various pieces of digital design. Michael, what's changed to the point where now we have to put together these pieces in a design that we didn't have to do it before?
I'm not sure it's anything that's really changed, but it's just continued pressure from customers on driving quality of results and time to results. Uh, Customers are always looking to do things faster and better. What we're enabling is a flow for digital design that achieves 10% better quality of results and 2 times faster time to results.
Why'd you draw this out for us?
Sure.
So what are we looking at here?
So Ed, if we look at the design flow, one way to depict it is the way we've drawn it on the whiteboard. We have synthesis, we have place and route, we have the sign-off products really along the bottom of the flow, and then we have test products, which I can illustrate on the left-hand side of the flow. And then between each of these areas, you see that we've called out design fusion. Design fusion exists at the intersection between synthesis and place and route. ECO fusion, as another example, exists at the intersection between place and route and our sign-off tools. And then we have sign-off fusion, which really wraps around the synthesis and place and route steps and connects our sign-off products into those two steps. And then test also does similarly between synthesis and place and route. It connects our test technologies and integrates them.
When did this become absolutely essential to do? Was it a creeping type of problem where you started out at 28 and it got worse at 16, or has it just started at most advanced nodes?
It's been a creeping problem. It becomes worse as we go to the most advanced nodes. But whether you're designing at 28 nanometers or 20 or 16, customers are still interested in achieving the best quality of results in the fastest time to results possible.
What does this buy you in terms of confidence in your design?
In terms of confidence in the design, you have a more predictable flow, one that concludes faster, 2 times faster, and you have greater confidence that you're going to achieve a better result in terms of power, performance, or area.
This is pretty much happening at the very front end of the design. Then you have verification, which happens at the back end. Does this help the verification as well?
It really has less of an impact on verification. It's really all about the implementation. It's ensuring that what you're designing gets done faster for the implementation phases of the flow, and that it's also of higher quality.
Another facet of this is not everything is being done on one chip anymore. Sometimes they're being done in a package. Does this apply there as well?
It does apply to the package. As we look to 3D IC and 2.5D IC type designs, what is being discussed here from an implementation standpoint would apply there as well.
Let's dig down a little deeper into what's happening in the flow here. How do these pieces go together?
So we look at the common technologies between synthesis and place and route. As synthesis has gotten more physical, you need placement technology. You need a global router. You want the timing infrastructure and the extraction infrastructure to align with what's happening between synthesis and place and route. And by doing that, you eliminate surprises in the flow. The way a design looks in the later stages of synthesis, converges as one passes into place and route. One of the other things that we're doing in the flow is we're taking the QOR technologies in synthesis and we're moving these, or in place and route, and we're moving these into synthesis. We're taking synthesis QOR technologies and we're moving it into place and route. And the reasoning behind this is if you were going to construct a flow that enabled the best results possible, you would not want to let the previous product boundaries constrain you too much.
With the most advanced nodes, you're also dealing with things like many more processors, different memories that are there, contention for memories. All this is absolutely essential to reflect in other parts of this, right?
Absolutely. I think as we look at the complexity of today's designs with multi-core type situations happening on chip, you got greater memory content in terms of the number of memories. It's important that the flow itself can comprehend and deal with the planning aspects of doing those types of designs and doing it in a very convergent way.
There are a couple of themes that run through advanced designs these days, one of which is process variation. How does it deal with process variation?
You're eliminating variability that can exist from having just different tools in the flow. So you have a singular analysis backbone that begins in synthesis, goes all the way through place and route, and so there's help there. As we look on our roadmap with static timing analysis and extraction, we look at sub 10 nanometer nodes. We do see greater variability. Our focus there is to extend what we've done in terms of cell variability into the interconnect to enable designs at 5 nanometers and below.
And variability has a lot of different causes these days and a lot of different implications for a design, one of which has to do with power as well. Where does power fit into this?
You get the power that's being consumed in the chip can cause thermal gradients across the chip. These thermal gradients then can introduce variability in terms of the timing performance of the circuitry on the chip. So this needs to also be comprehended as we pass through the design process.
Where does analog and mixed signal fit into this? Because now you're talking primarily about the digital design here.
So that's a good question. We have a custom platform as well where we're leveraging these same fusion concepts, integrating, for example, extraction technologies inside the schematic and the physical design processes, integrating physical verification technologies as well.
What happens on the test side?
As we consider the more advanced types of compression structures that customers want to put on chips, it's more and more critical that the architecture of these compressors can be directly integrated as part of synthesis to ensure that there's not too much congestion being added into the design and that this enables a more convergent flow. So we're taking all of our DFT technologies, we're integrating them in synthesis and place and route to enable a convergent flow there. And we're taking our Spyglass DFT test technologies, which enable RTL checking for test so that can be performed at the beginning of the flow.
And test has become a much more integral part of this whole thing. In the past, it was sort of an add-on that you did later on, right? Now it has to be done all the way through this.
Yeah, exactly. Starting from RTL, you need to be thinking about tests from day one in the flow. You need to be performing checks to ensure that the RTL is testable. Then as we transition into the flow, the complexity of the test structures are much greater than when we just did scan type test in the past. And so this needs to be integrated in a way that it does not disrupt the design in terms of its timing, power, or area. And it also needs to be routable so that you can converge the design quickly in the back end.
DFT used to be something that you didn't really think about. Now this has to be done way at the very front of the design, right? Almost at the architectural stage.
Exactly. It needs to, because the structures themselves that are being inserted can be more disruptive to the fabric of the design. So this needs to be considered from the beginning. And the fact that it's actually integrated as part of synthesis is we're actually optimizing the logic and considering concern about things like the timing, the area, and the power of the design. We can do this in the context of the test structures so that we are able to arrive at the best result possible.
Is your fusion approach, is this it? Is this as far as it goes, or will there be more pieces in the future?
This was a strategy we embarked on a little more than a year ago. And for the next several years, we're going to be building on this whole fusion idea, because today we are in the midst of, for example, integrating timing technologies from PrimeTime into IC Compiler 2 and into synthesis. We're doing similarly for extraction, but we're bringing more and more of these technologies on our roadmap and integrating this as part of the overall platform. We also have our exclusive partnership with Ansys, where they're providing the IR, the thermal types of analysis, and we're making these available as part of the overall platform, integrating into place and route and synthesis.
So for customers that have been working with us, what have you found?
We're seeing in the design fusion area, customers shaving 5%, 6%, upwards of 10% better area, better timing, better power from designs. And in terms of the sign-off fusion work that's being done, in terms of the integration of the analysis backbone and place and route synthesis, we're seeing a more convergent flow, one that requires less margin in the design process, and for that reason, we can even push PPA even further.
And is most of the work being done at 10.7, or is it a different node?
Most of the work that's, in terms of the application of this, at this point, I would say is at 16 nanometers and below. We do have design work that's being done at 7 and below, but we also have it as at less advanced nodes like 16, 14.
Michael Jackson, thanks for a great explanation.
Thank you, Ed.